Welcome back to the shop. It's good to see you again. You probably noticed I've had a bit of a tidy up, so let's have a quick look. I want to try something out, so I think I'm going to have a little experiment. Yeah, let's do that. The whole point of this exercise is I'm working on the auto crash system on this router, so that if the tool touches any one of the metal hold down clamps or any of the metal parts, instead of just breaking the tool and ploughing into it, it will instantly just go into Estop, stop the machine. I thought that would be quite a sensible thing to do, having over the years run over a good dozen hold down screws and clamps. So what am I looking for something that says bearings and springs. Yeah. Also going to need this. Excuse the aeroplane outside. Right, I've been through and I found a shaft. This came from an old printer along with most of the bits and pieces you see here. And I've got a bag of oilite bushes and bearings in here. And I found oilite bushes that fit this shaft, the other end, and a bearing that fits this shaft. So over to the lathe and we'll carry on this experiment. This is a bit gritty, so I think I might just soak that and see if I can get the remains of the grit out of it. Right, so I'll soak this bearing in Thai green curry and isopropyl, or denatured alcohol as I think it's also known. So I'll pop that in there. Over at the lathe, I think I'm going to change these spinny jaws of death, because my fingers are going to end up being quite close to this, to the collet chuck, which is less likely to mangle me. Not impossible, but less likely. Some of these chucks can be heavy. Deary me, look at the rust that I've managed to get on there. Never mind. It'll do. Not going to bother putting the locking pins in, because this is just an experiment with something, and don't know if it's going to work. And 32 collet chuck, that'll do. Right, so this is the shaft. Oh, there you go. Oh, that still fit. Yep, job's good. Let's turn her on. Look at this. I'm just getting my DMM out, and I came across this. My son borrowed this toolkit. He tells me he was using it to lever something up. It's a good job I have a spare. So I think that's such a sweet little hammer. I think I'm going to keep the head. So this one goes in here. Right, onwards. I'll just show you this. I didn't realise this till the other day. this thing, this lead says it's fused. So I thought, really? And I found you could unscrew it, and blow me, there's a fuse in it. I totally and utterly disagree with that. If you break that fuse, you could test a circuit thinking that it was no longer live because the meter would display no volts, and you could end up touching something that's live because this thing has got a broken fuse in it. I think that's utterly preposterous. That's lethal. Anyway, moving on. So here we are at the jolly old lathe. Let's test this. That's the only thing I would say. Every single time you use one of these meters, put it onto resistance and just make sure that the leads work. So let me clip onto that oilite brush, and I'm guessing, there we go, we have pretty much 0.001 of an ohm. Nothing. Now let's start the lathe up and try the same thing. Yeah, that works consistently, that's good. This is a bearing that I wouldn't use for anything important because firstly it's second hand, it's unshielded, and it doesn't sound very good. Right, let's add this to the shaft and see what resistance we get. Right, here we go. We all know resistance is futile. There we go. Ohms, nothing. A little bit more sporadic. Now my guess is, because there's absolutely no lubricant in this bearing, once I start the lathe, it's still going to read a 0. No, it's gone up. About 0.3 of an ohm. Yeah, 0.3, about half an ohm covers it. Okay, let's turn that off. Next up, I'm going to put some grease in that bearing. Right, put that back on the lathe. I'm going to run this for 10 minutes and get that grease nicely distributed in the bearing. So here we are, nearly 1 cup of tea later, and that bearing, oh, yeah, that feels like a proper bearing, apart from being a bit sticky on the outside. So let's carry on this experiment. Right, 0. Pretty much. There we go. Depending on where it settles, that's pretty much 0. Actually, it's going to be easier if I use these, so let's just clamp those on. I'll change that to a alligator clip. There we go, so just clamp onto there. Hopefully you can see that meter. Actually, let's put it so you can definitely see it. Damn it twice, damn it thrice. Right, if I start the lathe up, let's see what happens. There we go. I think what's happening is the grease is distributing itself properly around the ball race so that the balls no longer make connection. That, I think, there you go, I think that kind of sums up the situation with the router. I think that's the problem that I had with trying to make an auto stop for this router. It's perfectly that's the tool is connected to the base of the machine whilst it's stationary. As soon as it moves, the grease in that minute gap between the ball and the race fills that space. I mean, it must be down to sub-microns, but it fills that space nicely, stops the bearing from wearing out, which is good, but also isolates the bearing. So I've been looking to see if I can find some grease to use in that in those bearings that will be conductive. So this is what I've found. You can get a grease that's electrically conductive, and when I started to do the research, I thought, what on earth would you use that for? But actually it makes sense. If you ever go to a gym and you get on a treadmill, that's basically a Van de Graaff generator, and the static could build up on the belt to the point where it could, well, it might not end well, shall we say. So it could throw you off the machine or shock you, or people with bad hearts could have problems. So so this electrically conductive grease is there to allow the charge that builds up on the belt to dissipate through the bearings to the base of the machine. In other words, short-circuiting it so it doesn't build up. However, it's ferociously expensive and very hard to find here in the UK. You can also get graphite impregnated, graphite impregnated grease, which is black, and it's I think that's used for high temperature applications. And you think, oh, that might be a good idea. So I got thinking, and I came up with this. This is graphite powder lubricant. This is really to lubricate locks. You put it on your tiny bit on your key, and it makes the key slide into the lock easier. However, it did occur to me you can use this stuff to make things conductive. So you can, if you want to electroplate something, you might be able to use dust this over the surface, rub it in, create a conductive layer that you can then plate over. So I believe, don't quote me on that. So I wondered if I used some of this and mixed it with the grease in a bearing, if I could make a bearing conductive whilst it was being used. So I think we'll have a go. So the first thing I'm going to do is put it back into my Thai green curry isopropyl and put a drop more in actually, and see if I can get that grease out so we can start with a clean bearing. And we'll just try this lubricant by itself to start with, although I don't think that would be a sensible solution. So let me give that 10 minutes to dissolve. Might have to try something a bit more astringent. That doesn't seem to be doing the job. If anybody's got a second-hand ultrasonic tank that they don't need anymore, I'm all ears. Useful for this. Slowly eating into my desk as well. Oh dear. Anyway, let me finish my cup of tea while that green curry matures. Yep, that certainly feels like a bearing devoid of grease. It's not the best, is it? Right, we know, because we've just seen it, that this will make connection, goes up from 0 to about half an ohm when it's running. So let's squirt some of this stuff in, which I have to say is filthy. I've put a lab jacket on and a gloves, as you can see, because this stuff just does not come out of anything. And I'm supposed to be taking the Duchess out this afternoon. And I'm too lazy to change my clothes. Right, to the lathe. Don't know if you can see that, but look, it's already, my fingers are going slightly funny. Anyway, right, let's have a look. Let's do the same test conditions as before. We'll just clamp this on. Oh, not enough pressure. There we go. Right, 0 ohms as we'd expect. Well, there we go. Whoops. Hopefully you saw before that fell to pieces that the bearing is still conductive when it's running. So that's good. The only thing is I don't know if that lubricant, that graphite powder is any good. So I'm now going to just put a little bit more grease in there, run it again and see if that helps. This is an almighty sticky mess. This is interesting. That it started off with a quite low resistance, and it's been climbing up, I guess, as the graphite gets broken down and distributed a bit more evenly in the with the grease, and we're up to about half a mega ohm. Oh no, let's drop down to kilo ohms again. It's very inconsistent. Don't know if I can work with that. I'm going to leave it to run for another 10 minutes and see what happens. Right, I've been running this now for about 10 minutes or so, and we're quite consistently at about half a meg or 500 kilo ohms. That might not work for what I want to do. Yeah, I'm gonna have a think about that, because that it might possibly work. At least now I now have a connection, whereas it was completely isolated. But at 500k, that might be too high, because the lower the resistance, the more the better the noise immunity when you use an Arduino to pick up any touch for the tool. So yeah, I'm going to take the Duchess out to lunch and have a think about that. It's been a few days, 2 or 3 days, so let's fire this up and see what we get. Right, as expected, it's a short circuit now, and as soon as you move, it's no longer a short circuit. Let's turn the lathe, let's turn the lathe on and see what happens. Ah, that's interesting. Gone straight into overload, which means it's an open circuit. Interesting. Very interesting. That, I think, tells me, I think it tells us all, that what I'm trying to do here, make a bearing conductive when it's running, is going to be too difficult. Just for completeness, I've put the bearing and the spindle in the router, and weirdly enough, on the resistance setting of the meter, as soon as you connect one lead up, it picks up a voltage. So there's definitely a bit of a voltage between the ground and the spindle. Let's see what the scope says is going on. Right. This channel is connected to the ground of the machine, and this channel is a probe. Let me focus that up, because that's well and truly out of focus. There we go, that's better. Right, so let me have a little, if I connect onto the spindle, there's definitely something on that spindle. Digital noise, probably. There we go. There you go. Right, final test. If I probe the bearing and then turn the spindle on, we'll see what we can see there. Yeah, still lots of digital noise. This is plan B. I've got in this little vise, right at the back there, is a brush, a carbon brush from a motor. That's held in this little vise and it's pushed against a pseudo tool, a bar in other words, and it's down in here is a teeny little spring, and this my parallels box, which is I'm using as a weight. So that's pushing that brush against, and reframe that, that's pushing that brush against this pseudo tool. And I have connected 5 volts to my table bed, this isolated layer, which is connected to all of the threaded inserts in this bed. So that is a simulated hold down bolt, and I have put, there's my 5 volt power supply that's there's my 5 volt power supply that's feeding the bed, and it's also connected to the ground of the machine. And here's my oscilloscope. That is currently sitting at 5 volts because it's monitoring what's going on here. So the scope is connected to the bed here, and the scope ground is connected via this separate probe just laying here at the back, connected to the brush. So if I simulate that tool crashing by touching the hold down bolt to the tool, as I do that, it goes down to 0, which is what we want. And hopefully you can just see, it's out of focus I know, but it's difficult to do this with 3 hands. Hang on, let me have another go. There we go. Now I've focused it up, you can probably see it a bit better. As I do this pseudo touch of the tool, you can see the power supply dropping to 0 as it goes into current mode, and you can see the scope trace dropping to ground. So that works. However, that also worked with a bearing. So the issue to do is to try it when it's moving. So I've got this running at a low speed. That's its minimum speed. So the brush is clearly still, let me focus it again. So the brush is clearly still making contact. We've still got 5 volts on the meter. We've got 5 volts on the scope. And let me speed that up so it's a bit more. There we go. 5 volts on the scope and 5 volts on the power supply. So if I do the same thing and trigger a crash, a tool crash with this scriber, we go down to 0.8, 0.9, about a volt. There's some little bit of noise on the scope, but it's definitely registering it, as you can see there, and the power supply again trips in and out of constant current mode. I thought I could do it with an elegant solution of making a bearing, the bearing, there's a angular contact pair at the bottom, and there's a single bearing at the top, and there's very light load on that single bearing, so I thought I could fiddle around with it and make it conductive with graphite paste, or making a graphite paste or conductive grease. Conductive grease is really hard to find. You can get it for switch contacts, but I've no idea if that would stand up to the use of a spindle that can do 30-odd thousand RPM. So I decided I'd have a go by mixing some graphite with it, with the grease. That's a non-starter, that doesn't work. And you may also say, well, why don't you just use the oilite bushes that you've been using for a rotating connection? The same thing applies. I don't think that oilite bush will last very long in a 30,000 RPM spindle. So this is the fallback position, is to use a carbon brush from a motor. They're cheap as chips, they're readily available, not a problem. The only difficulty is the available space I've got in the back of this motor housing is tiny. So I'm going to have to crack that open and see what space I've got in order to fit some tiny little brush system in there. I also want to try and make it so that it's relatively easy to replace, because the brush will wear down over time. If I make the metal surface that is going to contact on the spindle really polished, then I'll minimise the wear on it, but it will still wear. So it has to be something that's easily fixable, relatively cheap, but more importantly reliable. So now I think I've come to a consensus. This is the only way I think I can do it. I'll put all this stuff away. Hang on, bloody bugs crawling on my legs. So I'll put all this stuff away. We'll crack open the top of this spindle and have a look and see what space is available. I think that's probably the next sensible solution. Okay, onwards. Right. Oh, that's not as bad as I thought it was going to be. This is a left-handed threaded screwed cap that basically keeps the spindle in and keeps the pressure on the bearings. And I made that, and I didn't make a very good job of finishing it. So I think I'm going to have to take that out, put it in the lathe and polish that flat. I've been on the internet and I cannot get a replacement brush set for one of these miniature motors. So I've decided I'm going to butcher one. And I've been through my bits and pieces, and it seems a shame to do this. It's got a nice little gearbox with it, but needs must. There we go. So that has a couple of nice little brushes in it. Here we are. We've got two little sprung brushes that will be ideal for what I need. Let's just see if we can get these out. Two brushes, and there's a Mark 1 finger for scale. When I moved this machine down here to this new workshop, I took off this gas spring, basically because it's no longer sprung. Its spring has sprung. So this should support the weight of the head. I think that the weight of the head is causing the stepper motor there to to miss steps. So I bought, a while ago, I bought a new gas spring. This isn't quite the right size, however this one is 300 Newton. Basically that supports almost my weight, so I reckon I need one that's a fraction of that. So I guess the net result is I'm going to need to order another one of these, which is going to have to be modified, I suspect, to fit, because it isn't quite the right length. I say it's not quite the right length. It might well. Oh no, it's when it's fully extended. It's not quite long enough. So, yeah, I'll have to get on with that. In the meantime, I'm going to risk this and hopefully. There you go. Look, if I line that end up, you can see that this end isn't quite long enough that way. So in other words, it won't let the head go all the way to the top of its travel. So I really do need to find a suitable replacement. Anyway, on with this. So let me re-establish. Let's rewind that code. Go to Z. Clean that down. There we go. That is now 14mm above the start height, the top of the part, because this pin is exactly 14mm in diameter. So now I should be able to just hit cycle start again, and we'll see whether or not it's going to do the job. Certainly looks like it's about 1.5 to 2 mil above the surface, which is where it should be, and that's about 0. Yep. Here's the top of the spindle, and let's just try this. I've been fettling, so I do know it fits properly. There we go. That's nice. And the brush sits there like so. So yeah. My next challenge is to drill a hole through the brush so that I can screw it in. Right, I've got it on the drill press and I've clamped it with a couple of toolmaker's clamps. So in theory, there we go, we're through. Excellent, I'll just snip off the extra bits. that M2 screw goes in from the bottom because I don't have any flat flat screws. So there we go. That goes, whoops, in like so. The brush goes on the top. This is the top of the spindle, and this brush will just rub on the top of that. Perfect. Right, we're back at the spindle, and as you can probably see, I've put back in the top cap and put some tension on it. So now it's just a question of pushing this down and seeing if we can lock it in place. Yeah, it looks good so far. Well, I have to say, that doesn't look too shabby. Let's try turning the spindle on and see if it mangles up this brush. That's a no, that looks fine. So here's the experiment. I've got the power supply over there. Ground is connected to the body of the machine, the natural ground. The supply is set to 5 volts and it's connected to the isolated bed, this aluminium foil layer that's in the middle here, via this screw. The multimeter is also connected to that and to the ground of the machine. So I've just clipped on here onto a rail, and as you can see it's 5 volts. So if I prop that up, perhaps you can be able to see that. Can you see that? Just let me know. Anyway, that says 5 volts. The machine is running, and I can simulate a short circuit by touching effectively, if the if the spindle were to run into a piece of metal hardware that's bolted to the bed. I don't know if you can see that particularly well, but that goes to, when I touch it on, it goes to 0 volts. Now I can't hold that on there when this is rotating, so I've got a brush that I can use, and as you can see it still works. So let's turn the spindle on, and we've got 5 volts happily there. As soon as it touches, it goes down to 0.1 of a volt. In fact, it goes down to next to nothing. Off, 5 volts, connected, damn near 0 volts. That's close enough to 0 to trigger an Arduino to say that's a negative, that's a logic 0. Okay, so let's run it up to maximum speed. That is shifting, that's about 30,000 RPM, so let's try it there. Yep, goes down to under 1/10 of a volt, that's for sure. This spindle has now been running for well over half an hour. Can you see that? You see that says 5 volts there? Let's try it. I have no idea, I haven't tried it yet, so let's see. Yeah, about 0.6 of a volt. It's slowly increasing. Oh no, no it's not. Half a volt. That's close enough, I think. So we're over at the laptop. I've written the code for the little Arduino. This is an Arduino Uno, I think, basically because it's what I had in stock and it's cheap. and connected to it is a relay block. So the relay block just takes power from the Arduino, so 5 volts and ground, and this little brown wire is a signal wire that that turns the relay that we're in question on and off as required. The only other 2 connections are that's ground, and that is the bed. So I'll change the lens so you can see closer what's going on here. Now I've brought you in closer. The Arduino is just looping through. I think I got it down to 9 lines of code. And the reason that I've reduced or kept the code as short as possible is because it loops. So it goes through each line of code, then back to the start and loops through. So the faster that it can get through the loop, the more times it will read the input, the bed, and see whether or not it's had a touch. So this is what happens when the bed, when the spindle, the tool, touches the bed like this. It triggers a relay. That relay's gone off, and we're waiting now for 10 seconds, and it'll then reset itself. There we go. It resets itself after 10 seconds because once the machine is held in Estop, I found this before, it prevents you from doing anything. So the only way I could get it out of Estop before was to turn the machine off, turn the router off, manually move the axis that pulled the tool off the bed, and then it could be refired up and start again. So I've made it so that it turns off after 10 seconds. Now here's the other. So there's 2 modes basically. When you touch an intermittent touch, it will wait 10 seconds, then revert back to normal operation. You can then use the control pen to take it out of Estop. However, which is more likely the case, if it stops and the tool is still touching the metal hold down clamp, it's crashed, it will still time out. There we go. After 10 seconds, even though that's still connected, it will time out, and then you can take it out of Estop again. So hopefully that should do the job. Let me move this over to the router and we'll have a go. We're over at the router, and I've temporarily wired this thing in, and it didn't work. It was triggering all the time. So I got my scope out again, and I had a look, and sure enough, there's an awful lot of digital noise coming from the control panel on the, control cabinet in the machine. And the noise is coming from the stepper motor drivers and also the VFD driver for the spindle. I've had a fiddle around, I've checked all the earthing, I've checked everything's grounded the way it should be, and it's good enough. So I can't make any improvements in the cabinet. So I thought, okay, what I can do is drown out that noise. So what I've done is, there's a big power supply in here, and I'll show you a picture of that in a second. There's a big power supply in there that drives the stepper motors, and it sits at 70 volts DC, and it's clean. It's a nice clean power supply, a pretty beefy supply in fact. So I thought, okay, if I take that 70 volt feed and then put a potential divider chain on it, because I can't put 70 volts on the bed here because it's deemed as dangerous. It's got to be 50 volts or less. That's the general rule. 50 volts is considered safe to touch. So I've got 3 resistors. The first one takes that voltage down to 50 volts. Then it gets applied to the insulated bed, and the 50 volts is then subdivided again down into 5 volts. So the 5 volts can trigger the Arduino, and I thought, that's good. However, this is the interesting thing, and I can't quite get my head around this, is the noise level is constant, independent of the voltage. So at the 50 volts on the bed, the noise level is exactly the same as it is as 5 volts when it's been divided down. I'm at a loss with that. I really don't know what to think. So if anybody's out there got a really clever idea as to how to get rid of that noise or minimise its effects, I'm all ears, because I'm just stumped. Anyway, having said that, it does work. So let me show you. I'll show you on the scope first, and you'll see what I mean about the noise levels. Right, hopefully this makes sense. That line is ground. So if I turn that off, this is a 10 to 1 probe, so it's 20 volts per division. So 20, 40, 50 volts. Okay, so and there's the noise level. So if I go to AC mode on the scope and just look at the noise level, there we go. Right, we've got a noise level of 1.2 volts, which is actually 10 times that. That's 12 volts. That's at the 50 volt level on the bed. So now if I move the scope probe, right, we're now on the 5 volt side of, this is the signal that goes to the Arduino, and it's exactly the same. So just to prove that, if I go to DC, there's our ground, there's DC, 0.5 volts, 5 volts per division, it's actually 4.6 volts, so that's where it sits at, 5 volts. The noise level's the same. How spooky is that? I would have expected that noise level to have been, because we've effectively reduced its level by swamping it out by the higher voltage. I would have expected that noise level to be about 1/10 of where it is. Weird, don't understand that. In the control cabinet, that's the VFD for the spindle. This is a 24 volt power supply for the electronics. Down here are the 3 stepper motor drivers for X, Y and Z, or Z for our American viewers. Further down we have a big beefy 70 volt power supply, and I've taken a feed of that 70 volts off. And right at the bottom here is the rich auto control system, and just incidentally a bus bar for the earth. So let's follow these wires up. These wires go to this tatty old breadboard. So I've set up a potential divider system. Sorry, so you can see that. There we go. Let's focus you up. So I've set up a potential divider system down here, and the 50 volts. So we get 2 taps on it, 50 volts and 5 volts. So the 50 volt goes off to the bed and is connected to the bed via that. The 5 volts goes off to the Arduino via this yellow wire, and that is the pickup for the tool crash. So there we go. So let me test this by simulating a crash with my little test probe here. All this does is connect the bed to the spindle. That's all it does. So that should trigger it, which it does. So holding it on triggers the e-stop. The e-stop will stay in position for 10 seconds, then resets, as you can see. So that all seems to work. But the noise issue is definitely a problem. Well, I think I'm going to have to call this video for here, because if I'm to keep to my upload schedule, this is Friday morning, this goes out Friday afternoon, so early evening. So I need to go and hit the post production and get this done. Thanks for watching, I do appreciate it. Please do hit the like and subscribe bells and buzzers, and this is very close. Unfortunately, I have run out of time, so bear with me. The next time, or maybe if I get it done a bit quicker, I'll do a short update at some point earlier than the next 2 weeks. But yeah, it's underway. And if anybody's got any idea as to how to lose some of that noise, digital noise, I'm definitely all ears. I think the thing does work, but whether that works reliably enough for you to be able to leave the machine and think with a degree of confidence that it's going to complete the task before going into a spurious e-stop, then yeah, I'm not convinced. Anyway, take care and we'll see you on the next one. Ta-da!